Welcome back. Today we're going to talk a little bit about some basics of machine learning, the machine learning workflow. We're going to talk about some terminologies, and we're going to see how optimization can be useful in performing machine learning. So let's first talk about machine learning. So machine learning means learning from data. Okay, so we want to learn useful pattern from data. Formally, we assume that we have a collection of data points, training data points or samples, which I'm denoting them by Z1 through Zn. Now, it is instructive to think of these ZIs as a collection of, let's say, some features and their corresponding labels. Okay, so a data point of this specific structure. For instance, xi can be thought as a vector with p features. Okay, for instance, an image that has p pixels. Okay, and yi we think of it as the label for the ith sample. Okay, for instance, if our sample is an image, y could be 1 or 0 to note whether that image is an image of a car or not. Okay, but this is just one example. We deal with data of different forms in practice. For instance, we can have collection of sentences, and our labels could be whether the sentiment in that sentence is positive or negative, right? We can have collection of videos. We can have collection of nucleotides, anything, okay? But to keep things more abstract, we're going to denote data points with ZIs, mostly in this course, right? But it is helpful to think of it as a collection of, again, features and their corresponding labels. Now, this is our workflow. So we have the image, we feed it to some model, and that model is going to help us to determine whether determine some useful patterns that we can later on generalize to new data. Okay. Now, typically, ML problems can be of one of the followings. So we have supervised learning problems where our data has the form that we have a collection of, let's say, features and labels. So we have labeled data in particular. Unsupervised learning is a kind of machine learning problem where our data is not necessarily labeled. Okay, so we will still want to learn some useful pattern from the data, but we don't know, for instance, whether that image is an image of a car or not, or is that image is an image of a cat or not. We don't have that information. And finally, there are reinforcement learning problems, where the idea is to leverage data to make decisions, especially in uncertain environments. And this is a very advanced topic, and it requires its own advanced course as well. All right, but let's see how we can do this a little bit more mathematically. So as we talked about in the previous slide, we assume that we can learn this pattern using some model, in particular using deep learning models. So let's see what we mean by that pattern, okay? So what we're assuming essentially is that there exists some true but unknown relationship between the features and labels, okay? In particular, you can imagine that this unknown model is A star, okay? So therefore, you could think of learning as the problem of learning A star from a collection of training data points, from a collection of features and labels, okay? Now, to do this, we're going to resort to a parametric model, okay? So A, which depends on some parameter W, that we want to find by leveraging data, okay? So the hope is that there exists a set of parameter W star, the best model, if you will, such that my parametric model is going to be a really good approximator of this true unknown relationship between the features and labels, okay? Now, how are we going to find this W star? As I said, we're going to leverage data. So in particular, we're going to perform training, meaning that we're going to fit the model to the training data to find the best possible set of parameters, W star. Okay? How do we do this? We're going to use optimization. In particular, we're going to design some loss functions, which here I'm denoting by L. It depends on the parameter W. And Zi here means that this is the loss of the model W fitting the IS sample. Okay? So we're going to leverage these loss functions, define optimization problems, and solve that optimization problem in order to perform the training step of machine learning. One example of the training loss is the simple quadratic loss function. Essentially, it captures using the quadratic function how well our current solution W is able to fit the training data. If it's a really good fit, we expect this to be near 0. If it's a bad fit, this is going to be somewhat large. So hopefully, by performing training, we can ensure that the model is going to fit almost all of the training data well. Okay? So to ensure that we perform very well on all data points, collectively on all data points, what we're going to do, we're going to define this optimization problem, which focuses on minimizing the average loss over the training data. Okay? So essentially, the most simple form of training is to, again, design a loss function and minimize the average loss over the training data to ensure that on average you have a really good fit to the training data. And once you do that, you'll find, let's say, a solution W star, and that will give you a good approximation to this unknown true model that you don't know, but you aim to find. All right, so that's training, and if it's done successfully, that means that we're going to fit the training data well, okay? But that's not the end of the story. We also want to ensure that we're going to perform very well on unseen data, on new unseen data. Essentially, we're going to make sure that the patterns that we learn during the training step are generalizable to data that we haven't seen, okay? Now, this step requires some assumption in order to assess whether the performance of the model that we learn by training is going to be good on unseen data. Essentially, whether training is a good idea or not. One assumption is to assume that the new data that you're going to be tested on and the training data belong to the same universe, okay? And that's not a bad assumption, right? So if I want to test my model on some data, some new data, and I have access to the data set, right? So let's say a set of images, those images better have some relation with the data that I'm going to be tested on, right? So if I'm performing training, let's say the images of cats and dog, and then I ask you, and in a test I'm going to give you, let's say, the images of whales, obviously that's not going to perform well. So it is a reasonable assumption to assume training and test data, or the new data, if you will, have some relation. In particular, you can assume that they belong to the same universe, okay? More mathematically, here is how we show this. So let Z be a new data. Then we say that Z comes from the same distribution that determines the training data. So in particular, Z comes from distribution PZ, and the training data, D, also comes from some distribution P sub Z, okay? And we call this data distribution. Now, what's our measure of performance? Well, for training, our measure of performance was how well we are doing on an average over the training data. Here, your measure of performance, which is a natural measure of performance, is to check how well you are doing on average over the entire universe, okay? In particular, this notation, the expectation over Z, you should think of it as, again, the average over the universe, okay? So not just the average over the training data, but average over every possible sample that I can be tested on, okay? Now, I'm going to denote this loss function with F bar, and this is in contrast to the loss function that we use in training, which I denoted by f. And it is important to know that f and f bar are not necessarily the same. In particular, f, the loss function that we use in training, is just an empirical approximation of f bar. All right, let's first see a simple example to sort of see the connection between f and f bar, okay? And in this simple example, I'm going to assume that the distribution of data is discrete, and essentially I have a discrete word. Okay, so these are my data points. These are my images, if you will. Z1, Z2, Z3, etc. And I'm going to sample one of these, let's say, with probability 1 over n. So in particular, this means that it is equally likely, at test time, it is equally likely that I sample one of these data points and I test you on that data point. Okay, so it is equally likely to observe each and every one of these samples. In other words, the probability that I select sample Zi is nothing but 1 over n. Now, let's calculate the functions f and f bar. In particular, the functions that we use during training, f, and the function that we're going to be tested at, f bar. So, f was nothing but the loss over the average loss over the training data. Okay, so I assume that my training data is essentially the entire universe. So therefore, f is nothing but the average over the training data. Okay, average loss over the training data. On the other hand, f bar was the average over the entire universe. And this was essentially how we note that down mathematically. Okay. Now, given that our universe is discrete, and it is equally likely that I observe each of these samples, so in particular, it's observing probably 1 over n, I can easily write down what this expected value is. Okay. So the expected value is essentially, so sum over the entire universe. My universe is discrete and I have n elements. The probability that z is equal to zi and the loss of fitting the ith sample, okay? And this probability is nothing but 1 over n. That means that this is going to be 1 over n, sum over I from 1 to n of L WZI. And this is equal to, perhaps not surprisingly, F, the loss that we use in training. So this basically says that if your universe is discrete and you are able to observe every single one of those elements in your training data, you can perfectly learn that universe, or you can perfectly learn patterns that are applicable to all elements in that universe by minimizing the training loss. Okay, but obviously that's not typically the case in practice. So even if I have access to billions of images, that doesn't necessarily represent the entire universe of images. All right. Now, there are some terminologies here, again, distinguishing between what we can do in training and what we can, or we hope to do in general on nuancing data that I'm going to briefly talk about. And that's basically the distinction between population and empirical loss. Okay? So, as we talked about, to ensure that the performance on all data points, all images, right? So, whether I see them in my training data or not, is good, we aim to minimize what we call population loss or population risk, okay? And that is essentially what we talked about before, minimizing the average over the entire universe. However, all we can do is practice to minimize the empirical loss, okay? And that's essentially the loss over the training data. And the reason for that is that, first of all, we don't know the universe, right? Or mathematically, we can say that we don't know this distribution, we don't know the data distribution. This approach, where we minimize an empirical approximation of the population risk, is called empirical risk minimization, or ERM. So let me pause here, and in the next lecture, we're going to talk about some sources of errors during the learning process that we need to understand and control. Thank you.